And of course, no session on planets, no conference can end without astrobiology. So the last talk is going to be on astrobiology, and it's given by Manuel Güdel.
Okay, last science talk. I'm standing between you and the boat trip. But I'm doing my best to finish within 45 minutes, I hope so at least. I would like to thank the organizers for the wonderful conference, but also, of course, for giving us a chance to talk about this subject. And the audience I would like to thank for staying so long. It's another 45 minutes. Here is my team. This is a mixture of experts in various fields. What I'm trying to bring together is, of course, a mixture of things. It's atmospheric science, it's X-rays, it's EUV from stars, it's dynamics, it's magnetospheres, it's atmospheres, and so on and so forth. So I'm talking about astrophysical conditions for habitability. Of course, we have all seen these plots here earlier already in the conference. This is a compilation of Kepler results. You see here equilibrium temperature and then the planets that have been identified or candidates. And more or less what we're interested in is, of course, this region here, a few hundred Kelvin, surface temperature, effective temperature. Of course, there are many more factors that come in, but more or less we're looking for planets that are somehow located here. Of course, we have the Earth in the midst of it. Now, whenever we talk about conditions for habitability, it doesn't take long, and that's what we're actually discussing. What is life? I'm not going to address this question. There's a lot of speculation. These animals with big eyes and green teeth and I don't know what else. We're not discussing speculation here. We have to define somehow what we mean with habitability. And that goes back to basically what we sort of know on Earth. So we have to confine ourselves more or less to see what the conditions are that make life as we know it possible. And that has, of course, has a long history, a long debate where we can form life as we know it. Now, factor number one, I would say, it's been pretty difficult to think about life forming in an atmosphere and floating there. We probably need something like a liquid or a solid surface, so we're definitely going for Earth-like planets. That's number one. And I'm not going to discuss about Jupiter-like planets in my talk. The second thing, and that's debatable, of course, our life forms on Earth are carbon-based. They need water. Chemistry needs water. Water is a wonderful molecule. It really has the right properties. So why speculate about something we don't know? So I'm going to define habitability based on water, as most people actually do. That concept has, of course, led to this often seen graphic here, the habitable zone. The Earth is in the midst of it. Mars is sort of inside. That depends a bit on the definition. Venus is definitely not in the habitable zone as we define it nowadays. Well, I want to talk a little bit about progress that has been achieved in the past decade or so. There's, in fact, new calculations for the habitable zone. This is a paper that just came out by Koparapu and colleagues. It's a bit complex. This is not stellar distance. You have different spectral types here. This is effective stellar flux at the surface or at the top of the atmosphere. So this is actually a little bit bent here. It depends on the spectrum that comes from the star. It matters how much infrared fraction you have in the light, in the bolometric spectrum. But anyway, these are definitions. That's actually an empirical definition based on Venus as it is, and assuming that it once had an ocean. That's the important calculation, runaway greenhouse limit. That's the state when a planet that has water basically loses it by the greenhouse effect and then eventually photodissociation of water and loss into space. So this is actually now moved very close to the Earth. 0.99 astronomical units, but don't fear that you slip into it in your lifetime. The problem is really that also these calculations aren't complete. I mean, there's cloud formation, there's a lot of cloud physics that has not been completely treated in these considerations. Venus, Earth, this is of course the Sun. Then we go out to Mars. The important limit here is the maximum greenhouse. You dump as much CO2 into the atmosphere as you can and see whether you can keep it warm. and then it ends at some point. Of course, Mars is inside because it can keep water if its conditions were right. Okay, new development has been the discussion of hydrogen. Hydrogen can actually act as a greenhouse gas, and surprisingly well so. There's new work that came out by Wordsworth and Pierre Humbert this year. And the speculation is, well, you just add hydrogen, molecular hydrogen, to a nitrogen atmosphere. You need to have a relatively dense nitrogen atmosphere. But then you can get greenhouse effects. And in fact, before I explain it here, there has also been previous papers that don't do nitrogen, but do hydrogen molecules only. Then you need quite some pressure, actually. For example, for a super Earth, you can do a 40-bar hydrogen atmosphere. This should actually be 10 astronomical units here. What you get on this plot here is an extension of the habitable zone out to about 10 astronomical units, out to Saturn's orbit. Now, of course, we have to demonstrate whether such atmospheres exist and whether such planets are around. But interestingly, we'll come back to the hydrogen atmospheres again later. So this is an interesting development here. Good. So far about the classical definition of habitable zone. This is a necessary condition. This is not a sufficient condition. And what I'm going to do in the remainder of my talk is really discussing additional components of this whole issue of habitable zones. What happens is that we have dynamical conditions, we have other conditions related to atmospheres, related to the central star, and so on and so forth. Now, a lot of this has, of course, been discussed in previous chapters, and very extensively. I haven't written it here in the chapter by Jean Raymond, transport of water from the outer solar system to 1 astronomical unit. Now, what has not been mentioned so far, not extensively been mentioned, I just want to bring this up as an example. Of course, it matters what the dynamics has been doing to the solar system over the whole evolution. But that's not the only thing. You can, of course, transport planets into the habitable zone and do good things to them. A big problem is you eventually need to decide how your solar system looks like, where you park the giants. And that's sort of been addressed this morning by Melvin Davis. But I want to show you an example how delicate this really is in our own solar system. What you see here is stability calculations between Earth and Saturn. Of course, the whole rest of the solar system is there as well, like Jupiter and so on. This is the semi-major axis of the Earth. Earth is here. That's the semi-major axis of Saturn. Saturn is here. And then we sort of begin to vary these semi-major axes. And what you see here in color is the eccentricity of the Earth when you begin to change things in the solar system. What happens? Let's shift. This banana here actually shows a region of relative instability. It's not unstable, but you add a lot of eccentricity to the Earth orbit. Let's shift Saturn from where it should be, 9.5 astronomical units to 8.7 astronomical units, and then all hell break loose. This is an unstable, it's a region where massive secular perturbations take place. It's from a resonance between Jupiter and Saturn, but it's mediated to the Earth orbit. And what's happening is this. That's a plot showing the time evolution of the eccentricity of the Earth orbit during 30 million years under these conditions. Well, here is the Earth eccentricity. It goes up, if you can read this, 0.4, 0.5, 0.6. That's not really what you want to have for a habitable orbit of the Earth. This takes you out to beyond Mars and takes you in very much. For millions of years, you have this orbit. That's not nice. Now, you see, you have to adjust the parking place of Saturn very carefully. Otherwise, the Earth doesn't really do a good job. Something else that I want to add, sort of, because a lot of discussion has happened about transport, especially in John Raymond's talk, did a great job showing us where the water is coming from. There's a piece that's sort of missing. It's great if you have collisions and interactions between bodies, but you need to transport that water. You have collisions and you're not sure whether that water sticks. This is sort of an ongoing work here by the team in Vienna. We're doing lots of simulations. This is not a hydro simulation. I'll run it again in a few seconds. This is an SPH simulation. You need to do SPH. You need to do solid-state simulations with cracks and all that stuff. You can't do that hydrodynamically. It's a 300,000 SPH particle simulation. I'll just run it again. What you see here are two Ceres-type mass planet asteroids or planetesimals. One comes with a little water on the surface and the other doesn't. The question is what happens to that water? And this is just one of the simulations, first one at the moment. You see the collision here, the water is in blue. And in fact, what's good to know here, there's a lot of deformation, lots of defects taking place in these bodies. But the good news is actually that you can, and this is just one example now, you can keep the water on the bodies and transport them successfully into growing bodies. This is now not one that in which the bodies stick together, but there will be other simulations of this kind. Now let me move to a totally different aspect, and that's the central star. Everybody says, of course, yes, there's a central star, and it's a spectrum and whatever. What is it actually doing? Fundamental calculations using the standard solar model show that the sun has become brighter in the past 4.5 billion years. It actually became quite dramatically brighter. This is the modern solar spectrum, optical, near ultraviolet, and then it sort of dies away here. If you go back to 0.7 gigayears, 700 million years, what we see is the sun was actually considerably fainter. It was at about 75% or so. So it increased in evolution, and of course it also increased a little bit in temperature. Now, you may say, well, okay, it got a little bit warmer. The problem really is, it got not only a little bit warmer, that's what happened with the sun. It increased in radius, it increased in temperature a little bit, and that's what should have happened with Earth at the beginning of the solar system. You can't possibly have an Earth with warm climate and liquid water. Well, you can, but you have to play a lot of tricks to do that. So how do we get out of this? We know that the Earth was different. We know also that Mars was different. It's more dramatic for Mars, of course, because it's at a larger distance. We know from zircons, we know from oxygen isotopes, sedimentary rocks and geological structures, there was a warm climate at that time on Mars and on the Earth. That's also known as the faint young sun paradox. It's been discussed for about 40 or almost 50 years. There's no solution really, but there's progress, and that's good to know. What people have begun to do, well, of course, all this discussed are additional greenhouse gases. You can add methane, you can add ammonia, that's been discussed for 30 years or so. But new molecules have come up. I don't want to go through all of them. This is not about the faint young sun paradox here, and this is more like atmospheric chemistry. But anyway, most of these solutions that are coming up now periodically have their own problems. Some of these molecules dissociate, others form hazes and absorb sunlight again, and it's a really complicated story. For Mars, there's a particular problem. You would like to add carbon dioxide, of course. There's a lot of carbon dioxide on Mars anyway. This diagram that's back quite a while ago from calculations from Jim Casting, you see here adding carbon dioxide pressure on Mars as much as you want in your simulation. And then you see here the insulation that you need to keep Mars warm enough for liquid water. One is the present day level. And as you see, you can add something like 5 bars of carbon dioxide atmosphere to Mars, and you successfully drive it warm. You need only about 85% of the luminosity of the sun. That's great, but you should go back to 75%. That's not visible here. So that's been a long-standing problem. Carbon dioxide doesn't do the job. You need to add other things. You may want to add, in fact, as has been discussed, as I have discussed just a few slides ago, and I'll come back to this again, maybe you want to add hydrogen. But then you have to demonstrate that this actually worked. Lower albedo, you can add also can add high ice clouds. They trap radiation, they warm an atmosphere. Or you get fewer clouds lower down, closer to the surface. For example, by reducing the condensation nuclei, there's been work. Why there should have been less or fewer condensation nuclei in the young Earth. This is controversial. It's a big debate about whether you can solve that problem. Good, so that's the sun. That's the photosphere of the sun, visible light, 6,000 degrees. Now we move up in the sun to higher levels. That's the chromosphere at 10,000 degrees, seen in the ultraviolet light. Move on to 50,000 degrees, transition region. Again, ultraviolet, we go to the EUV, 600,000 degrees, you see coronal structures, this is all in magnetic fields, and finally at 2 million degrees also EUV and X-rays, you see the beautiful corona. That's what really happens on the star. Now what happens on the planet in the light of this mess that's going on here? Let me first go back to, well, from the corona back to the chromosphere. It's the same, taken at the same time. You see a network of bright things here and patches. Now that's really ultraviolet light that you get out of this. This is not coming from the photosphere. This is magnetic activity, magnetically heated gas. And that may add actually considerable emission to the irradiation spectrum. That's actually the modeled evolution as we see it from other stars. This is the ultraviolet and optical spectrum. I've already discussed this. That's actually 3 times in the solar history of the optical and near ultraviolet spectrum. It goes here from green to red to blue, 0.1, 0.7 to 2 gigayears. It becomes brighter, as we know. Now look what happens in the ultraviolet, in far ultraviolet, in the EUV. It's going the other way around. We have very high levels of ultraviolet and even more of EUV. This is normalized to present-day solar. It comes down, it comes down, it comes down very rapidly. But these levels were 100 times higher. I'll show you more higher factors in a minute. They were hundreds of times and tens of times brighter than nowadays. So we definitely have to take this into account. For M dwarfs, it's even more dramatic in a way. This is work by Kevin Franz and Jeff Linsky, different papers discussing the amount, the level of far ultraviolet radiation compared to near ultraviolet. Lyman alpha is specifically important. Most of the ultraviolet, far ultraviolet light is actually coming in Lyman alpha. You see here a compilation of measurements dependent on the spectral type, effective temperature of the star from G to M. As you can see here, this is the level of Lyman alpha in the habitable zone. It's normalized to the habitable zone of the respective star. You see here the sun. And you see the M dwarfs, almost regardless of age, they're all very active. They produce a lot of ultraviolet. In fact, they produce so much ultraviolet, you have to be careful with biomarkers. For example, this level of ultraviolet photodissociates CO2. You get abiotic oxygen 2, and of course, as a consequence of oxygen 2 and ultraviolet, you get ozone. So if you do M dwarf habitable zones and detect planets and you detect oxygen and even ozone, don't be surprised, it's not a biomarker. So really be very careful with this. Okay, there was a poster by Feng Tian who has added further good information on this. Of course, poster's probably not there anymore, but you can look at it when it's published. Good, why is ultraviolet so important? This plot here by Knossen and others shows the absorption cross-sections for different important molecules. For example, ozone is here. That's 250 nanometers. You get more here, carbon dioxide and so on. And here is what happens on the star. This is an M dwarf with no magnetic activity, very boring, there's not much here. But as soon as you go to the active M dwarfs, you get this high level of radiation here in the ultraviolet. Here's actually the solar spectrum, an F dwarf. But you see, M dwarfs actually have even more far ultraviolet than even the sun, present-day sun has. So this is a very important thing. Cell types matter, and you get a lot of ultraviolet flux in the habitable zone. Here's an example of what happens. That's a temperature diagram. You see here height in the atmosphere, temperature. That's the Earth temperature profile. You get this inversion here, and this inversion is related to, in fact, absorption of ultraviolet in the ozone layer. That's where you produce ozone, basically, by photodissociation of oxygen. Let me go back to an M dwarf. An M dwarf that has no magnetic activity doesn't do much. Temperature profile in the atmosphere of an Earth-like planet is basically flat here. And you go back and add ultraviolet, and interestingly, everything cools even. That's because methane is dissociated, and that has a cooling effect, essentially. It doesn't heat as much anymore. But now we add ultraviolet again, 10 times and 100 times, and you get this huge inversion. produce oxygen, dissociate oxygen, you produce ozone. And that can be seen in the spectra. That's now model spectra. You can actually see this ozone feature here that comes from this huge inversion. So the message here, I'm not going to more chemistry. I mean, time isn't here to really discuss this in more detail. But the message is, first of all, your ultraviolet actually determines the profile of the temperature profile of your atmosphere, or at least does part of it. It's very important. And second, it does a lot of chemistry, as we have already seen in the previous slide. So I'll leave ultraviolet here. There's a lot that should be discussed, but let me go on to X-rays. This is a collection of X-ray spectra actually measured. The sun spectrum would be about the blue one. This is not quite the sun, it's another star. 10 angstroms, 100 angstroms, here's ultraviolet. Now we go back in time. And these are really measured spectra. You go to younger and younger ages until you hit the 0-age main sequence, more or less. This example here. And you see how much higher that spectrum is. You easily go up by a factor of 1,000, if not more, in the flux. In fact, when you compare it with what I've shown before, X-rays, EUV, ultraviolet, optical, this is the time evolution approximately between the 0-age main sequence and 4.5 billion years. Here's the sun. You see soft X-rays show the most dramatic decrease by a factor of 1,000 over that whole time range. EUV is a bit less, factor of 100, ultraviolet, a factor of tens or so. Meanwhile, the optical radiation comes up by something like 30%. Now, why is this all important? Well, X-rays and EUV, of course, heat. They ionize and they heat the upper atmospheres of a planet. And they do that quite energetically. That's why you don't get the X-rays down here at the surface, but they're doing their thing high up in the atmosphere, and they're doing ugly things, as I'm going to show here. These are temperature profiles, and these calculations have been pioneered by Feng Tian. There's lots of papers about them, and he was probably one of the first ones who did it really right, shown here in this figure. It's a long history behind these calculations. There's temperature, altitude of the atmosphere. It's an Earth-like planet. This is the temperature profile on Earth. Get to about 800 degrees. You reach the exobase. That's the level where the mean free path of a molecule is larger or begins to exceed the scale height, the local scale height. So if that particle decides to be energetic enough, it can leave, goes into space, basically gets lost. And what happens here at the exobase, indeed, is that the highest energy molecules or atoms get lost into space because there is no collision anymore. Above the exobase, you get into a collisionless gas. You can't do hydrodynamics up there, it's just wrong. So there's so-called Jeans escape. The highest energy particles get lost, and you can calculate how much this is. The Earth's atmosphere loses gas that way all the time. Now we add more EUV. We go to 1.5 times more EUV than we get at present. Well, the atmosphere gets hotter, the higher atmosphere. It blows up, it gets higher and higher. The exobase gets higher, 1,000 kilometers. It moves up to almost 10,000 kilometers. It's getting very hot up there. And then suddenly, you see it doesn't actually move to the right anymore. It suddenly turns over and the atmosphere gets cool if you add 20 times the EUV level that we have nowadays. Now what's going on there? You dump more energy into it and it's cooler. If you analyze the simulation, you actually see that there is a flow. The atmosphere begins to flow hydrodynamically. And at that moment, people plug in a formula and say, well, okay, energy limited, and I don't know what, blow off. Blow off is the keyword, that's all wrong. Don't do that. It's not blown off here. This atmosphere is not cut off and blows away into space. What's happening here is a very delicate hydrodynamical motion of plasma, and the upper boundary is defined essentially can be defined by Jeans mass loss. There is an enhanced Jeans mass loss there, but it's not that the atmosphere is just blown away. What one has to do is really, it's only part of the particles that get lost through a Jeans-like loss mechanism, and the others are not actually blown away. Only when you have very high energies, you go very close to the star, you may actually begin to get into a regime where the temperature is hot enough that your whole Maxwellian is above the escape velocity of the planet. And then, of course, you have blow-off. But that's not so often seen. So blow-off doesn't really work. So you need to do hydro simulations, otherwise you don't get it right. In this stage here, in this middle stage, when you begin to have flows and adiabatic cooling, I should have said that. That's actually adiabatic cooling, that's why it cools. You need to do full hydro simulations, otherwise you may get it wrong by factors of tens, hundreds, several hundred actually, if you just use an energy-limited formula. Anyway, having said that, why is this important? Now we know, and we have heard it already, of course planets form in protoplanetary disks. There's a lot of helium and hydrogen gas there, and they accumulate such atmospheres. They accumulate gas from the disk. There's also outgassing, not only through volcanoes, there's outgassing as the magma ocean at the beginning of the Earth formation begins to solidify, and then a lot of gas is coming out. Estimates have it that disk atmospheres, I mean gas that is accreted from atmospheres, could be tens to hundreds of Earth-ocean equivalents. Wow, that's the amount of hydrogen that you have in an Earth ocean. Okay, that's often used in this community. Maybe up to 10 to the 4 times such an amount on super-Earth. Outgassing may bring you a few Earth oceans worth of water onto the surface of the planet, and that's something like 500 bars for an Earth-like planet. There are lots of literature here about this problem. That's great, okay? We have this dense atmosphere because that protects this feeble nitrogen atmosphere that we would like to keep until the present day. And I'm going to show you this is non-trivial. It actually has a protecting property and a good task in the early days of the planet. The challenge, however, is eventually we need to get rid of this hydrogen. It's not here anymore. And you don't want to live in a 100 bar, in a 10,000 bar hydrogen atmosphere. That's not so funny. We need to get rid of this. How do we do this? There's a lot of ongoing work with this, and there has been quite a number of publications recently about this. I'm just showing you an example how to go through this. This is a self-consistent calculation of how much hydrogen you can accumulate on a planet in a protoplanetary disk, given some boundary conditions. One of the boundary conditions is the temperature on the surface of the Earth, of the forming planet. And that temperature comes from the accretion of material. You could do some self-consistent estimates on this. Just give you the numbers here. Here the y-axis gives us the number of Earth oceans worth of hydrogen that are accumulated by a planet of one Earth, sort of here. And then, thus the mixture plays a role. But anyway, what we read of such simulations or such calculations is we get something like 50 to 500 Earth oceans of hydrogen. That's a lot. That's a really dense atmosphere. Now we need to get rid of this. Let's see whether we can actually manage that. Now what we next need are full models of the structure of a planet, from the planet itself to its atmosphere. And these calculations are separately done at the moment. There's the group by Christoph Mortosini. We have pioneered quite some of this, and they have a lot of calculations, and I'll show you some of them. We basically read off, this is the amount of hydrogen that we get from the upper plot. We can then calculate what for one Earth mass, the radius of that, the optically thick radius of that planet would be, of that atmosphere. And from then on, we go into hydrodynamic simulations. We take this as a boundary condition and add hydrodynamics. And what's coming out is, dependent a bit on the radius that we have here, we take 100 times the XUV radiation of the present-day sun, 1 astronomical unit, 100 million years. What you get rid of is maybe 30 Earth oceans of hydrogen. Now, that's not doing the job, obviously, because we need to get rid of 10 times more in the worst case. So we shouldn't, of course, despair, because, it could be that way. Maybe it's realized in the universe. We may have these planets. That's a radius mass diagram for some Kepler and other targets. You see those up here, very low density, average low density planets. And those may be those with huge hydrogen atmospheres that have actually survived. But it was not the case in our solar system, obviously. We don't have that type of planet, at least not in the inner solar system. So either we just got it right, We didn't collect too much hydrogen, we just got rid of it, and we kept the nitrogen atmosphere on Earth. Well, that's good luck, I guess. Or maybe it actually just tells us that the Earth could not have assembled while still being in the disk to the size it has. So the assembly of the Earth must have, in this picture, occurred considerably later when the gas was gone. Otherwise, we would have this dense hydrogen atmosphere. Good, so I'm sort of coming to the final topic. There's something much more energetic going on out there, and that's the solar wind. As I already said, or I should say it very energetically now, nobody has ever seen a solar wind from another star, an ionized wind of that type, a magneto-hydrodynamic wind. It's very, very difficult to measure. There are indirect methods, and I would like to mention at least the one method that has led to quite some sort of detections. It's a method pioneered by Linsky, Brian Wood in particular. I don't want to go into explaining any of this. It's quite complicated. It's a lot of modeling work that is needed. What essentially happens is that between the interstellar medium and the heliosphere, there is a pileup of neutral hydrogen because of charge exchange between the two components. It's quite complicated what's going on here. But anyway, we have such shells around our sun. We have such shells around other stars. And if you look for Lyman alpha lines in the other stars, there's excess absorption of Lyman alpha. I don't want to explain this in detail, that you can see and can distinguish whether this comes from the astrosphere or whether this comes from the heliospheric hydrogen wall. And so one can estimate approximately what the wind mass loss rate is in those other stars. What's coming out is this relation here. This is surface flux density in X-rays. That's sort of an activity indicator. These are very young stars. These are old stars. That's about 700 million years, age going to the left. That's the mass loss rate. And indeed, here's the sun. Indeed, going to younger stars, one infers an increase of the mass loss of the sun by a factor of about 100. Unfortunately, we would like to know what's going on when the planets form and the atmospheres come up. And that's very messy here. Now, either you believe that, as measurements tell us or want to tell us, there are no winds or very feeble winds, or, well, something else is going on here, like the winds go in different directions or are polar or I don't know what else. Or the magnetospheres are somehow closed by strong magnetic fields. That has to be figured out. We don't really know. Anyway, why is this important? Now, magnetospheres, in fact, protect atmospheres. So we have a protection mechanism once again. But what's also happening is charge exchange between the solar wind ions and atmospheric neutrals. If you don't have a magnetosphere, this happens anyway. This happens all the time, of course. Solar wind goes into the atmosphere, there's charge exchange. What's coming out is an ion. That will be wiped away by the solar wind. It's getting lost. That's basically a loss mechanism. So you carry away a lot of, atoms that become ionized. The other particle, the ion, becomes a neutral, and it becomes an energetic neutral. And that's, of course, also important to realize, because you have a lot of energy coming here as neutrals, and they can go and stick into the atmosphere of the planet. I'm not saying much about this anyway. This can be calculated, this process. This is new work by Kislyakova and others. It's somewhat complex. This is a star here. This is below exobase. That's not been calculated. Here's a magnetic obstacle. Now you have magnetic fields. Magnetic fields, of course, prevent this from happening all over the place. It can only happen outside the magnetic field. The wind comes from the right, the green dots here. And anyway, what's coming out are the blue and red dots, and these are the high energy, the neutral atoms, the energetic neutral atoms. And they may actually go back into the atmosphere of the planet and do additional heating. Now, what's been calculated in this example here is actually the mass loss through ions that come from the surface of the planet and then go through charge exchange, because all of them that make the magnetospheric boundary here, they're carried away by the wind. Now, in this example, that's around an M-dwarf. It's an Earth-like or super-Earth in this case, around an M-dwarf in a habitable zone. The loss is actually not dramatic. It's something like 10% of the thermal loss that I already discussed. So this doesn't really help to get rid of this hydrogen that I discussed before. You can add this, it doesn't matter. We still have a problem with the hydrogen atmosphere. On the other hand, there was a poster on this anyway. On the other hand, and that brings me back to the nitrogen atmospheres. This is a calculation that it's from Lichtenecker and others. I show you again the Tian plot for different EUV rates, and then this turnover here, where we have a flow of mass, a flow of atmosphere. Now, the magnetopause, the sort of end of the magnetospheric level, in the present-day Earth was here, and in fact, because of the stronger solar wind, it was compressed somewhat, so it was actually even lower. Now you see what happens if we, on the one hand, heat the atmosphere by adding EUV radiation, on the other hand, we enhance the wind and then compress the magnetosphere. We get to the level where this flow actually goes above the magnetosphere, and then it's all wiped away. So we have a new mass loss mechanism there as well, because the magnetosphere doesn't protect the atmosphere anymore. So it's a very delicate game here. Now, the calculations show this, and I don't want to go all through all details. This is present-day solar wind, 30 times stronger solar wind as it was in young ages of the star. Different XUV levels, very realistic, that could have happened. Then you go through these calculations, you integrate for 10 million years, 100 million years for the weak wind, for the strong wind here, the same. You see the numbers. It's a few bars of nitrogen atmosphere. It can be 50 bars of nitrogen. It's just blown away in no time. So what can we do? Well, actually, it's even worse in M-DORs. If you go for M-DORs habitable zones and you want to do this feeble nitrogen atmosphere, 1 bar, you better care about whether you get lost, whether it gets lost because of the wind of the M-dwarf. It's really very delicate. One solution, and maybe Venus has actually shown that, is adding carbon dioxide. With carbon dioxide, you get cooler here, you cool the atmosphere successfully, and maybe then the losses actually go down. That's one of the hints that the Earth's atmosphere was not a nitrogen atmosphere only when in the young years of the Earth evolution. Okay, I think my time is sort of over. Took you through some of the issues. And, the mandatory ALMA slide. I didn't find any very reasonable one. Of course, ALMA will contribute, but this is ALMA in New Mexico. It's a small town not far from the VLA site, by the way. That must be that way, right? ALMA and VLA. It even says welcome. This is actually a habitable place. It has a restaurant even, so, you know. Good. Concluding remarks. Well, it's a field that has seen a lot of activity for decades already. It started in the 60s, more or less. It's a very complex field because it's interdisciplinary. You have to add winds, X-rays, magnetic fields, the planetary atmosphere, the outgassing of the planetary atmosphere. Protoplanetary disks come in, and you have to sort of mix this and see whether you get the numbers right. And I think a lot of this needs to be still taken with care. It says it here, of course. This is actually at the VLA, just by the way. Take it with care. The numbers change. It's delicate. It seems to be sometimes like fine-tuning is needed to get it right. It's not very clear whether all planets behave the way you want to have them behave. And definitely, when we talk about habitability, there's, of course, the issue of life. I didn't actually talk about life. Of course, what is habitability in the end? It's not only water, it's a lot else. We don't exactly know. So these are soft edges of this whole field of research. Okay, and with this, I want to close here. Thank you.
Questions? Hans, go ahead.
Manuel, here. I have a question about the magnetic field of the Earth and its importance and related to the liquid core and the radioactivity. So the word radioactivity didn't occur in your talk. Is it important?
Yes.
The size of the core?
Yeah, intentionally I did not address these things because we really wanted to confine this presentation to astrophysical factors, really factors coming from the outside, from above, if you will. So yes, of course, magnetic fields are important, and the generation of magnetic fields and radioactivity. I don't want to talk about radioactivity. That's not our expertise. I really don't know much about it, nor the team is not working on this anyway. So geophysical factors are important. For example, magnetic fields. And there's a lot of debate whether magnetic fields, how they have been in the early time of the planet. Earth has kept it, Mars hasn't. We know that Mars had a magnetic field, and it actually had a magnetic field in the crucial time when all these things happened. And it may have been some protection of Mars, indeed, in the early times. But then the magnetic field disappeared after a few 100 million years, and that, of course, produced some problems. There's also the discussion whether magnetic fields are important in habitable zones of M-dwarfs, because there's some speculation that the orbit or the rotation period of the planet is bound. Well, it is not speculation, it's probably bound. But then you wonder whether you can form a magnetic field, a dynamo, and there's also research going on. There was originally thought, well, there's no dynamo, no magnetic field, or not much of a magnetic field. That's not quite true, because you can have convective dynamos that do the job anyway. So it's all a bit uncertain how much you have in terms of, Venus doesn't have a magnetic field, unfortunately. So
very good. John, up there, you have a question?
John Debus, Space Telescope Science Institute. Your point about M-dwarfs being very active is well taken in terms of the impact on habitable worlds, but I wonder what fraction of M-dwarfs are really active enough for it to be a problem, and I imagine that this changes with time, so
yes.
M-dwarf lifetimes are long.
Yes, it does. There are inactive M-dwarfs. If I said they're all active, I exaggerated. Of course they decay, and it's really spectral type dependent. Early M-dwarfs can really become inactive, after several 100 million years or so. And it really depends on the spectral type. You can easily carry on for a few giga-years with being highly active, dependent on the spectral type and the rotation period, of course, that goes with it. So there are the inactive M-dwarfs indeed. But it takes a long time. And if you see these simulations, these atmospheric simulations, I didn't talk much about timescales, but this really happens early on. This happens on timescales, evaporation of atmospheres, of bars and bars of atmosphere. This happens on timescales of tens of millions of years. And now we have this star that is active for 1 billion years. I mean, you blow away all the atmosphere anyway. So you have to be very careful with M-dwarfs.
Very good. Please go ahead.
Hi, Manuel.
Hello.
You talked about a lot of things, but there's one other thing you didn't talk about that always strikes me about the Earth, and that's that it's an Earth-Moon system. And the collision that presumably formed the Earth-Moon system may have had a big effect on those early atmospheres that you were worried about. So I wonder if you have any comment about that.
You mean impacts, or?
Yeah, well, as I understand it, the Earth-Moon system formed from a giant impact.
Yes. Yes, of course it was important, but that's a specific example for the Earth. Of course, could have lost a considerable part of the atmosphere. But I didn't go into specific simulations. Of course, it does matter, but there's no systematic study that I'm now. Of course, for the Earth, yes, but not for other planets. Not aware of any systematics.
Very good, please.
Adam Frank, University of Rochester. Two things. One is just a comment. In talking with Jim Casting, I was amazed to find out how much our own problems with the climate change have to do with these new calculations that we're right on the edge of the warm or the moist greenhouse effect. That's just an interesting aside. But I wanted, you didn't mention anything about habitable moons. I'm wondering if you just, obviously it's a huge field, but just how much of this carries over, how much is different when you have to take into account conditions for a moon?
Well, again, of course, that's a very wide field because you can construct interesting cases. Titan is one that you can construct. Titan with a hydrogen atmosphere would be an interesting place to live, actually. Well, we don't know whether it's an interesting place to live. What's coming additional to that is magnetic protection. Titan doesn't have to care about magnetic protection because Saturn does all of it for Titan. So that matters as well. Of course, there's a whole issue about, of course, you can have a giant planet in the habitable zone. It's not interesting for life, but the moon, planet may be interesting. You don't want to do it in the environment of Jupiter because you have high energy radiation. So you have to be careful there again, because these huge magnetic fields around giants may actually disturb habitability on the moons. But then you can go inside the moons, and we explicitly excluded that discussion. Jupiter's moons, Europa or Enceladus around Saturn, that's another type of habitability, and you really need to distinguish that because it's maybe interesting, we don't know much about it, and you can't observe it. And that's the basic point why there's not so much being done for extrasolar planets in that field.
Very good, please.
Hi, this is Feng Tian from Beijing, China. Thank you for mentioning the work of mine and my colleagues. Appreciate that. About the hydrogen greenhouse, although maybe hydrogen and nitrogen collision-induced absorption may help to increase the surface temperature, hydrogen, like carbon monoxide, are actually good food for bacteria. And on the Earth, methanogens is one of the earliest form.
Yes.
They like to eat hydrogen and release methane. And if that were the case, then the existence of hydrogen and CO in the planetary atmosphere is actually an anti-biosignature. So what do you think about that?
Well, I mean, basically, the question is whether you can get rid of the hydrogen atmosphere that way.
Well, the energy that hydrogen can provide to the life form, bacteria, is pretty high. They favor hydrogen, so they eat it away.
Yes, yeah, well, that's nice, but it stops when the hydrogen atmosphere is gone. So,
exactly. So there's no greenhouse effect from hydrogen anymore. So hydrogen can't help with the climate.
Yeah, I agree.
Okay. If I may, another thing that...
Wait.
Okay.
Please, go ahead.
Hi, Duncan Forgan, University of Edinburgh. Somebody asked me, I'm right here, hi. Okay. Somebody asked the question earlier about moons, which I was going to ask, so I'll just add a comment instead. So you've talked exquisitely about how the host star and its properties affect the habitability of your planets, but there's another factor as well, which is how many host stars you have. So there's been some recent work on how binary systems have a very complex habitable zone morphology. So I was wondering if I could get your thoughts on that.
On binaries in general? Yeah. Yes. There are numerous solutions that you can get. Initially was thought, well, you know, habitability is a difficult issue in binaries. It's actually not really. First of all, you need a stable orbit, and there are lots of stable orbits in binaries. But then you have to watch out for a complex type of interaction. I mean, there's of course a dynamical interaction between the components and the planet. And there is light from a second sun, so to say. Now, what matters is perhaps not so much the irradiation from the second star, but what the second star does in terms of perturbation to the orbit of the planet. And then the orbit of the planet sees less light from the primary star as well. So the secondary may actually influence the variation of the light that comes from the primary. That's an aspect that is being simulated indeed. But the simple answer is, yes, you can get it. There are habitable zones around binaries. Depends on the type of binaries. You have planets around the binary or planets around the primary or secondary star. And there are lots of solutions that do produce such habitable zones. It's not excluded at all. There's ongoing research, indeed, also in our team, that investigates this to more detail and sort of maps all possibilities that you can have. Can't give you numbers now, but it's definitely a very interesting field that is being developed and further developed. Of course, large work has been done already.
Very good. So we have time for the 3 remaining questions, and again, I would appreciate short answers.
Yes.
Please, go ahead.
Thank you. Sean Matt, University of Exeter. Thank you. It was a great review, and I just wanted to point out one more uncertainty, as if you needed any more, which is you pointed out very interestingly that the activity of the star can have a big impact, in particular the high energy radiation, and the fact that this evolves in time. A lot of the estimates you had, for example, that the X-rays for the sun were up to 1,000 times higher. That's really kind of an upper limit. We don't know. At the zero-age main sequence, observationally, solar mass stars have spin rates that range over almost 2 orders of magnitude. So we don't actually know yet if the sun was only rotating 4 times faster or 100 times faster. And so the point is that, as that's very important for habitability, the rotational evolution of the parent stars may actually be important for habitability.
Yeah, absolutely. Fully agree. I mean, this was sort of an average level. If you go into exoplanets, you don't know, you can't know the detail there. You assume an average level. That's what it is. A particular case such as the Sun, we really don't know. We don't know the solar history that well. There are indications that the young Sun was active in meteorites. You can actually sort of trace it. It was certainly not an inactive star. That's what we know.
Very good. Please, Andrew, go ahead.
Hi, Andrea Jean from MIT. I have a quick comment and a question. So let me start with the comment. I'd like to advertise my work, if I may. So if you have a planet which has a smaller water reservoir than Earth has, and a smaller relative humidity than Earth has, then such planets can be habitable as close as 0.4, 0.6 AU to the Sun, which is great because these planets orbit frequently, so they are easy to follow up and characterize. So the question is, you kind of calculate, you want to check how the stellar spectra influences the atmosphere, right? But in most of the calculations, you considered an Earth analog atmosphere with Earth-like composition, surface pressure, outgassing rates, and things. How robust are these results, and what happens if you change these parameters?
They're not entirely robust. I mean, I showed at least one indication in one of the early slides. I'm not sure how long it takes to get back. It is spectral type dependent. If you do the calculations for, to calculate the limits, such as the water ocean evaporation, the spectrum actually does matter. And you see a spectral type dependence. I mean, maybe go back, but it's a long time back to the initial talk. What you have to take care of is infrared radiation. You have a high fraction of infrared in M dwarfs, and that makes your habitable zone move out. And that's sort of been seen here in this very early plot. No, I should just bring it up. I hope I can. So spectral type does matter. It of course matters for chemistry as well. If you have more ultraviolet, and there's more chemistry going on. Oh my goodness. It will come, I tell you. Here it is. I mean, these calculations are really in detail. They were done in much detail. And you see the flux, it's something like a 25% change dependent on the spectral type.
Yes, but what happens if you change the atmosphere parameters? Not the star parameters,
you mean the
but
atmosphere? Of course, yes, of course, it's dependent on the atmosphere.
What is robust then?
Well, it depends on what you mix in. I mean, if you have a nitrogen atmosphere, it does something. If you add a lot of carbon dioxide, the whole thing changes completely because it's a greenhouse gas.
Yep.
I mean, it's completely different. Yes, of course, these were examples. I cannot map the whole thing. So what I often assumes is, I mean, nitrogen is here. We had nitrogen in the early Earth, probably. Carbon dioxide is all over the place, so there was probably carbon dioxide. That's why people usually assume such atmospheres. They're natural. Well, you can do a hydrogen atmosphere, and it's completely different.
Okay, thank you.
Last quick question.
Hi, I'm back. So, quick question about that availability of elements required by life. It's good to know that current definition of habitable zone depends on the existence of liquid water, long-term existence of liquid water. But we are currently considering the existence or maintenance of nitrogen and other elements in the planetary atoms in the planets as a result of atmosphere escape, atmosphere loss precise. And we think that if you move down, if your star is lower in mass, it might be more difficult to keep nitrogen inventory, just as you mentioned earlier. But that may have some significant consequences on the habitability, both in terms of nitrogen availability and in terms of climate stability.
Yes.
So that's ongoing work right now.
Yeah,
Thank you.
I agree. Yes, thank you.
Very good. Let's thank our speaker today.